Okay, so today we'll start with the harmonic field theory. Rather, we'll introduce the harmonic field theory. So now, when we say fermions, the first thing we need to understand that what is the difference, primary difference of this field theory with respect to the scalar field theory that we have learned so far, right? So now, when I'm talking about the, let's say, for example, scalars or fermions or any other kind of, for example, photon, which is a gauge field and so on. So what are the primary differences between them? So immediately that comes to in our mind is the spin, right? So we know the scalars, which we dictate by, let's say, S, they have spin 0, and the fermion that we abbreviated by this F, we consider them to be start with spin half. Okay. In general, the fermions are considered to be half integer spin, but primarily our interest will be spin half fermions. Now, as you know, that spin half fermions actually satisfies this Dirac equation, and we'll see that thing in more detail. But what is more important aspect here is that the scalars, and when I'm saying scalars, the scalars are basically tell you they do not transform. Now, whenever we say in our mathematical language that something is not transforming or something remains invariant, that automatically tells you that you need to associate some kind of transformation property, right? And whenever there is some kind of transformation property, if those properties satisfy, transformation satisfies some kind of properties, then they can form a group. Okay. So the idea is there is some kind of group which is used using the language of symmetry, and that dictates you the transformation property. Now, when I'm saying the scalars or fermions, that means with respect to some kind of transformation property, and that particular transformation property is dictated by these Lorentz transformations. Okay. Now, these Lorentz transformations, based on what kind of field is transforming how under this Lorentz transformation, that tells you whether that object is transforming like a scalar or a spin half or a vector or some other higher spin. That means that spin, this quantum number, is basically associated with this Lorentz group. And how that we'll learn little bit later when we talk about more about the Lorentz group and so on. But at least to start with harmonic field theory, we should be able to understand the difference between this harmonic field theory and the scalar field theory in a sense of the additional quantum number which this kind of fields have in the form of spin, right? So at least we have now the idea that what is the kind of difference between the scalar fields and the fermion fields. And what we'll do, we'll try to replicate the structure of the scalar field, and there will be some additive and some additional components with that, and how they will carry the signature of the spin that we'll try to identify. So before going there, what we can start with our old Hamiltonian, which we write down as a H, and we can write down from the relativistic point of view, H as a p square plus m square, where p is your the momentum, right? And H is the total Hamiltonian. So now, if you think about the Schrodinger picture, and then H, you can equivalently write it down as the I del del T, right? And then P vector, it can be given the operator form as I minus that, right? So then, if you write down this equation in the operator form and you take a square root, what you'll get basically Dirac equation. Or other way round, if you write down the Dirac equation, okay, and if you square that operator, okay, you get the Klein-Gordon operator. And this is not an accidental thing. This is a very deeply rooted in the mathematical framework about how the spin half and spin zero things are connected, and right. So we will not go detail, but this is based on our observation only. So from the Dirac point of view, what we can write down in this particular form as the Hamiltonian is basically, if you write gamma 0 and then gamma dot p plus n. If you start with this operator, okay, and then you calculate the h square operator, and then what you find out the following: half gamma 0 gamma I, and then gamma 0 gamma z, okay, and then either you can put a plus, and this plus tells you, so whenever I have this kind of relations plus, this is equivalently, I will write down as the anti-commutator, or write down AB plus BA. So this is how I define my plus. So I can use either this convention or this convention. Okay, so you should be familiar with both. And then I have PI, PJ plus, you have a gamma 0, gamma I, and then the gamma 0 plus PI M, and then you have the gamma 0 square M square, right? So now, if I define my Hamiltonian in this particular form, and if I take a square of this Hamiltonian, I should get back to this structure. So if you do that, you will get some kind of relation between this, and this quantity. And what are those relations? If you follow gamma 0, gamma I, gamma 0, gamma z, plus equal to twice delta ij, okay, and gamma 0, gamma I, gamma 0, plus equal to 0, and then gamma 0 square equal to 1. So if these three relations are satisfied, then you can see I can get back that Hamiltonian that we started with the h square. Now the question is, okay, so we have noted, or we have identified rather, in this particular form, do they form any kind of algebra, or what about these gammas? So this gamma I, when I'm writing, this actually I equal to 1, 2, 3, and then you have a 0th component, gamma 0, right? So this, you can think of the spatial part, and this is the temporal part. So if I write down the gamma mu, this automatically contains your gamma 0 part and then gamma I part. Okay. So this is like, 3 plus, if I equal to 1, 2, 3, that means 3 spatial and 1 temporal. So we are working with 3 plus 1 dimension space time. And if you further decompose these relations, what we'll find out is the following: that if I combine this gamma mu in terms of gamma and gamma naught, then we find out gamma mu, gamma nu, anti-commutator is twice G mu nu, where G mu nu is your metric. And this is nothing but mathematical language is called the Clifford algebra. So I will request all of you to keep your mic in a mute. If you have any specific question, then only raise your hand and unmute. Okay. So now So this is the Clifford algebra. So we can see that for the fermion, there is some kind of new algebra is being satisfied, which is the Clifford algebra, right? And these gamma mu in 3+1 dimension, they are actually 4x4 matrices. Okay. And then the question is how this gamma mu and all those things transform and so on, that we have to see, and what are the other properties of gamma mu. So immediately we can check that trace of gamma mu equal to 0 for all mu. That means mu equal to 0 and all those things. And that can follow from trace of gamma naught is equal to minus trace of gamma naught, gamma 1, gamma naught. But also if you use the cyclic property, right? And from there, sorry, this is gamma 1. Cyclic property, from there you can show that gamma 1 square is basically minus 1. So these two are consistent with each other. Okay. And then we also can define some operator sigma mu, which will later see when we define some magnetic moment and so on. This kind of operators will be important, but I can define as the commutator of this thing. So this minus sign tells you basically the commutator, which is defined as gamma nu minus gamma nu, gamma mu. So look at the change in sign here. It's a commutator, right? That's why I put a minus sign. Okay. So now here another important gamma matrix is being introduced here, which is called the gamma phi.
Hello, sir.
Yes.
So why the trace of gamma mu is 0? Can you please explain?
Trace of gamma mu is 0.
Yes.
Okay. So that you should be able to prove from the previous relation that we have seen it.
Okay, sir. Thank you.
So that is not an assumption, that's an artifact of the algebra from the algebra itself. Okay. So now here we can define this gamma phi as in particular form of this, and then that is not an independent operator. You can construct as like this, or also in a much more tensorial form, mu lambda rho, gamma mu, gamma nu, gamma lambda, gamma rho. And this is a completely antisymmetric object. It is completely antisymmetric. Completely antisymmetric means that this is antisymmetric all its.
Professor, I think you should mute everybody and just like put it just we can just raise our hands and unlock the microphones. Otherwise, it would be
Yes.
very
Yeah. So can I do that? Mute on. Yes, I think now I've been able to do that. Okay, thank you. Okay, I hope my microphone is not switched on in the process. Am I audible? Please.
Yes, sir.
Respond in the please respond in the chat. Okay. Okay, thank you. Yeah. Right. Yes. So what I was saying that this quantity is fully antisymmetric. Now, one has to be very careful about that because we know there are some higher rank tensors are there which are antisymmetric between some of the indices. That's why there are some mixed symmetries and antisymmetries could be there. So if it is antisymmetric in all its indices, then we only call it fully antisymmetric. That means any two indices you pick up and change their positions, okay, you pick a minus sign. That's how you define this thing. Okay. Fine. So now let me spend a few words with this operator or this special gamma matrix, and then we'll move on for the further things. So this gamma phi is very special, and we'll see why. But let me tell you that is it necessary that in always you can define the gamma phi? The argument is for the scalar case, we did not distinguish whether our space-time is even dimension or odd dimension. For example, there are many conventional systems are there where you construct your field theory as 2 plus 1 dimension, right? But we are here talking about 3 plus 1 dimension. So there, it is not too much difficult to translate your 3 plus 1 dimension scalar field theory into 2 plus 1 dimension. But for the fermion, you have to be very, very careful. Careful in a sense that there is a notion of projections or the chirality, okay, when you are working in a even dimensions. So this gamma phi is a very interesting operator that we can use this gamma phi. We can add and create some operator using this gamma phi, which are called the projection operators. And this projection operator, the name is very clear as we have done in the quantum mechanics. If you remember, in the quantum mechanics, we have some kind of, the states are there, remember? And then we define this kind of projection operator. And what was the purpose of this projection operator? That this projection operator will act on some kind of state, and then they will project out the component of this state vector along some directions, right? So similarly here, in the fermion, in the event dimension, they are chiral in nature. There will be left-handed of chiral fermion and right chiral fermion. So when we write down a field theory, we write down the field theory in a specific chirality. Okay. So either you write down the whole Lagrangian in terms of the left chiral fermions, or you write down the whole action in terms of right chiral fermions. And sometimes this is misleading in a sense because many quantum field theory and particle physics book we use left and right convention same way. That should not be done, but unfortunately, sometimes we use that. But you have to keep in mind that if the total fermion dimension is twice n dimensional, okay, and then what you do, if they are chiral fermion, you will have n dimensional fermion which are transforming as a left chiral object, and other n dimensional object will transform as a right chiral object. So you will construct your theory either with the left chiral fermion or right chiral fermion, and these right chiral fermions are actually will not transform under the left chiral transformation. So when we talk about the Lorentz group in detail, that will be important. But keep in mind this gamma phi operator, the way it is being introduced here, okay, keeping in mind that gamma phi is basically not an independent one. Because we are working at 3 plus 1 dimension, which is 4, so it's even dimension, right? So gamma phi is not an independent operator, and that's why when you write down the algebra, this is the Clifford algebra. Gamma phi is not part of the algebra. Okay, you are constructing gamma phi using these 4 such gamma matrices. Okay, that's why. And when you can do that, gamma phi as an independent operator, not part of this algebra, then only you can construct a projection operator using this gamma phi. But what happens if we work with 4 plus 1 dimension? That means we are working in odd space-time dimension, right? In an odd space-time dimension, gamma phi is part of your Clifford algebra. Okay, then you cannot use that gamma phi. Okay, that you can give a different name, but let me call it a gamma phi prime. That gamma phi prime you cannot use to construct a projection operator, and that's why in an odd dimension space-time we cannot have chiral fermion. So we find in nature that chiral fermions, that is not accidental actually, that is mathematically consistent because our space-time that we are working with is a 3 plus 1 dimension, even dimension. So that's why we get a chiral fermion. Now, why this information is important? This information is important because when you construct some other UV theories, which is beyond the standard model and so on, then one has to be very careful that you should not start with a theory which cannot accommodate chiral fermions, right? Otherwise, you cannot get your standard model fermions out of that and then automatically falsify those kind of theories. To construct a consistent standard model extension of the theory, you must accommodate chiral fermions. So that's why this gamma phi in our fermionic field theory plays a very crucial and important role. Okay, and how and all the details of mathematical things we learn along with the Lorentz group representations. But yeah, conceptually, if you have any question, you can drop the question there. Okay. So now,
Yeah, I actually had one small question.
yes.
Yeah, could you please kindly redefine once why we can't have chiral fermions in the odd dimensions?
So in odd dimension, gamma phi kind of matrices are part of the algebra. So if it is a part of the algebra, then that Clifford generator or that matrix I cannot use to construct a projection operator. Okay, to construct a projection operator, I need an operator which actually is not part of the algebra. Okay, so that's an odd dimension, we cannot define that.
Okay. So we cannot define the projection operator in the odd dimension. That is the problem, I guess.
Yes.
Professor, I have a
Yeah.
question.
Yes, please.
So basically, following this discussion, you're telling us that we cannot define chiral fermions in odd spacetimes, but is it related to the fact that in the equation for gamma 5, in terms of the Levi-Civita symbol,
Yes.
we have that it's sort of a cross product, and cross products cannot be defined in cross products can only be defined in 3 and 7 dimensions. Is it related to that fact or is independent of that fact?
No. Okay, so this is the way we can write it down. Okay, but why we cannot define that? That is more from the representations of the Lorentz group or the Clifford algebra.
Okay.
Okay, so
Thank
you. Okay, so what I'm trying to say that this gamma phi, the way you are writing, we are writing here. Okay, now this is the generic way of writing. That means you can always write down gamma phi kind of operator in as a product of gamma matrices, but whether that can be used as a projection operator or not, that depends on the fact whether you are working in even dimension or odd dimension. Okay.
Yes.
Okay, thank you. So yeah, actually, I may not be able to always read the chat. So can you please speak out the question? That will be easier for me. Yes, so you are asking that, so the number of gamma matrices depend on the dimension you are working with. Yes, of course. Yes. So in fact, the number of gamma matrices also depend on the space-time dimension, and also you see that their inner structures will also depend on that. So maybe when we talk about the Lorentz group representation, then I will make a brief discussion on in generic D dimension how to write down the gamma matrices. Okay.
Yes.
Does that answer your question?
Yes, sir.
Okay.
Thank you.
Okay, there's another question. So there are 2 left fermion and 2 right in C++. Yes, exactly. So in 4th dimension, and that's why we'll see later that because the Dirac fermion, when you write down, you do not mention the chirality, right? Now Dirac fermion is 4 components, final we'll see, and that you can decompose. It's in a 2-dimensional left-hand fermion and 2-dimensional right-hand fermion. That's why we call it 4-component notation to 2-component notation. Okay. Okay. Any other question?
Yes.
Yes. No.
So what exactly is the difference between the chiral representation or the chiral basis and the Dirac's representation?
Sorry, I could not hear your last point. What is the difference between?
What is the difference between the chiral or vial representation or basis and the Dirac basis?
Okay. So when we write down the fermions in the 2n dimension, so to start with, you have 2n dimensional fermions, right? Let's say you start with a 2n dimension. Now, if it is chiral, then only you can decompose this and write down n left-handed chirality and other n as the right-handed chirality. But if you are working at odd space time dimension, then you can have only 2n dimensional representation, for example, but you cannot further decompose them or rewrite them in terms of left and right. So when I'm writing in this particular form, we call it a Dirac representation, and this we call the chiral representation.
Okay, so the Dirac representation, I'm sorry, the chiral representation will be the left and right representations, right?
Yes.
And
so
the
Dirac, once you project out the Dirac representations, from there you can construct the chiral representations.
And the Dirac representation is the most general one in which you have
Most general one, yes. Which satisfies the Dirac equation. So the fermion representation that satisfies the Dirac equation is the Dirac representation. You can think of that way.
Okay, it's the general 4x4 matrix representation.
Yes.
That's the Dirac one. Okay,
Yes.
thank you.
Does that answer your question?
Yes, thank you very much.
Okay. Yeah. Any other question? Okay. So let's proceed then. So now finally, so what we can find out that we can get a set here if we write down 1. I'll explain what are those. 1 gamma mu, sigma mu nu, gamma phi, gamma mu, and then gamma phi. Now, these are the different variants of these gamma representations you can write down. Now, what does this 1 signify? That this is when under the Lorentz transformation, this is transforming like a scalar, right? So that's why, it is not transforming at all. We can say that way. Gamma mu, when you will find that a gamma mu, this will transform like a vector. This will transform like a rank 2 tensor. This is transforming like a pseudo vector. Pseudo, sometimes you call axial also. Axial vector. Axial nature because of the gamma phi. Okay? Because gamma phi is very related in this particular notion with the parity. Okay? So that will be clear, but let's stick to this axial vector, and this is like a pseudo scalar. So now, whenever there will be Lagrangian, and then these kind of quantities you will find out in the sum of the term, the Lagrangian, you can immediately identify how those terms are transforming under the Lorentz transform. Okay, so that's are the independent 6 defined variants. At this point, we can identify. Another important property of this gamma phi is that trace of gamma phi is 0, and also it anti-commutes with all the gamma matrices. Okay, so that's how you write it down. Now, when we talk about any operator or any term, we know our Lagrangian is to be Hermitian. So we need to know how these gamma matrices transform under the Hermitian conjugation. So that you write down as a gamma mu dagger, as a gamma 0, gamma mu, gamma 0. Okay. And gamma I dagger, if you identify this, you can prove as this one starting from this. You just set mu equal to I, and then immediately use the anti-commuting nature of the gamma I and gamma 0. From there, this will follow from this relation. This is simple, you can put that thing. So now we are ready to write down our Dirac equation of all these things. So which we write down. Okay, another point that the G mu, if you remember, this is the metric in the clipboard algebra space. So that we can use, to raise and lower the indices. For example, gamma mu, you can write down as a G mu gamma mu. Okay, so these are the sufficient information, and whenever I use the symbol a slash, this implies that it is gamma mu a mu or gamma mu a mu, right? So this is the symbol that we'll be using. So from there, now we are ready to write down our Dirac equation in this particular form, which we write down the I del slash minus m psi of x equal to 0. Okay, and remember we are working in 3+1 space-time dimension. Okay, so then what we can do actually, we can transform and then see that if I perform the Lorentz transformation, okay, then how the things actually get changed, how the Dirac equation gets changed. So then Lorentz transformation, if we do, how we'll write down this equation? I write down the gamma mu del mu prime minus m. So m we define as a Lorentz scalar, so it will not change. Psi prime.
Sir?
Yes.
Yeah, in a Dirac equation, there will be a psi bar, isn't that? Like psi bar.
That's a
There will
Lagrange.
be.
It's an equation.
Yeah.
You can write
So,
down
yeah,
the
you're.
equation for particle as well as antiparticle. Okay, these are written in terms of psi. You can take a conjugate of that. You can write down for psi bar.
Oh, so we can write it in terms of both as well.
They are
Yeah,
not
okay.
independent. I can write it down for that. Yes.
Okay.
Yeah. So now this is basically equal to 0. So this is the Lorentz transform this thing. And then how these are related? So x prime mu is lambda mu x mu. Lambda mu are basically my Lorentz transformation informations are dumped there. So then I would expect that psi prime of x prime is basically s lambda phi of x. Okay, and here we assume that psi prime x prime and psi of x, they are linearly related. Okay, that's the assumption here, and this is the transformation property. So we need to find out what is my s lambda. Now if we plug it back in this equation and try to write down everything in terms of unprimed basis, so what we'll find out the following: gamma mu lambda mu del mu s of lambda psi of x minus x lambda psi of x equal to 0. And then we multiply. So you multiply by S inverse from left, and remember this direction is important because they don't commute. So here we are multiplying from left. So that will give me, if we have to satisfy this relation, gamma mu lambda mu is lambda to the gamma mu, and then only we can say my Dirac equation is basically doesn't alter under this transformation. If that demand we impose, then we find out this relation. And then S of lambda, what we can say that this is a infinitesimal Lorentz transformation if you find out, then we can write down lambda mu nu as a metric G mu nu plus some omega mu nu, where this is equal to minus omega mu nu, the antisymmetric part. Okay. So then we can write the rest of lambda as 1 minus I by 4 beta mu nu omega mu nu, and these betas are basically my 4 by 4 matrices, which we'll see how to write down in terms of gamma. And then S inverse lambda, we can write down as a conjugate of that is I by 4 beta mu nu omega mu nu. Okay. So this gives me the notion of beta mu nu, and then we'll find out if we set beta mu nu equal to sigma mu nu, then these all are consistent. So this is how you transform your states under the Lorentz transformation. This is the exponential. So you know the infinitesimal transformation, I can always exponential. So this I can write down as a omega mu nu psi of x. Okay. So this is how you basically transform, the states. Okay.
Professor, I have two
Yes.
questions.
Yes.
So back when you were talking about the bilinears, the direct bilinears, the pseudo-tensors, pseudo-scalars, pseudo-vectors, when you were talking about all of those,
So yeah,
So you can-
these are basically here. These are basically 6 different variants we will find out in 3 plus 1 dimension. In 3 plus 1 dimension, based on the Lorentz transformation, we have these 6 different quantities. Yes.
yes, so basically, my first question is about that in the sense that, okay, when we have a Lagrangian of a field theory, we can classify, because I've seen vector boson, scalar boson, or
Yes.
whatever. We can classify it with if our Lagrangian has one of these terms. So if my Lagrangian has scalar terms, so it will just describe scalar fields. If my Lagrangian has, if the interaction part
Yes.
has a rank 2 tensor
Yes.
term, for example, then I will have a tensorial quantum field.
Yes. For
And
example, that's certainly rank 2 tensor, you can think about, you can write down a magnetic moment kind of operator. Okay. Right. Or you can also, if you introduce a higher spin object, okay, they also transform with a higher rank tensor.
okay.
Okay, but though we restrict ourselves to spin 1, so then in that particular case, this kind of term, we'll see this signifies the presence of the magnetic moment kind of operator, which are not present in the tree-level Lagrangian, but certainly they can be generated additively.
Okay, so we could have rank like tensor interactions above tree-level diagrams, right?
Yes, in a tree-level Lagrangian, for example, if you think about the standard models, only you have these possibilities: scalars, vector, and this kind of thing. And on top of that, you can extend your theory, right? Then you find out you can have a pseudo vector or axial vector, okay, depending on the interaction. So these are all allowed. Whether standard model does have or not, that's a different question. But I'm saying these are all allowed by the representation theory.
What about the Lorentz invariance of the pseudo or H?
No, so these are basically under the Lorentz symmetry. So now if you want to violate Lorentz symmetry, then you can have many other options there. And they are not such as restricted, I would say.
Okay.
So these are having a consistent Lorentz transformation. These quantities have a specific transformation property. That's what I'm saying.
So parity, my final question is,
Mhm.
Probably a silly one, but I don't know. Does parity breaking, the symmetry breaking of parity then violates Lorentz invariance in some way?
Yes. So when you talk about spontaneous symmetry, I'll mention that why we need to stress on the choice of symmetry breaking field to be only scalar or spin zero. If you take a non-zero spin, that will violate the Lorentz symmetry. So we'll discuss that when we talk about the spontaneous symmetry.
Very interesting. Thank you very much, Professor.
Okay. Yeah. Any other question? Okay. Great. So now, there are some properties that I've asked you to check and perform the algebra, because and for the Feynman case, there's lots of algebras are involved. If you don't do it by your own, you don't get that feeling. So I would suggest to do these algebras. This is gamma lambda equal to 4, which are contracted here. Okay, and then you have a gamma lambda, gamma mu, gamma lambda equal to minus twice gamma mu. Okay, and then gamma lambda, gamma mu, gamma lambda is 4, g mu, and then gamma lambda, gamma mu, gamma rho, gamma lambda equal to minus twice gamma rho, gamma nu, gamma mu. And these are important because remember, at the end of the day, after understanding the field theory, our primary goal is to calculate the scattering amplitudes and all those things, right? So then those kind of, when you talk about the fermions and all those things, right? Like Hava scattering, molar scattering, and all those things, when we compute, we'll use these relations. So it's better if you just do these algebras by hand. So that will be really helpful for okay. So now about before stepping into the quantizations, I'll try to recall that how we introduce the solutions of those in the case of scalar field theory. So we start with, remember, the plane wave solutions because they're the free theories, right? And then we add on some kind of operators which are kind of a raising and lowering operator mimicking the quantum mechanics, and those operators later are upgraded in terms of the fields as the field creation and field annihilation, and similarly for the antiparticles as well. So here also, when we talk about the solutions of the Dirac equation, we'll mimic the similar way. We'll talk about the free Dirac equation, we'll solve that, and as expected, the solutions will be written in terms of the, plane wave solutions. But now, the plane wave solutions form, which we found out earlier, as e to the power IPX and e to the power minus IPX, depending on the positive and negative energy states, right? So they are, because they were the scalars, they were associated only with kind of psi and psi dagger, or phi and phi dagger kind of thing. But here also we have to keep in mind that these fields are related with the plane wave solutions, but now they must contain another wave function, which is the spin wave function. And that spin wave function was absent for the scalar case. So even before doing the calculation, if we want to, get an idea from our acquired knowledge that how does the solution look like, then we should be able to understand that the total solution would have two components. One is the plane wave solution, another is the spin wave solution. And those spin wave solutions, what you know as a U spinner and the V spinner. And this U and V will give you as a combinedly total the 4 component Dirac spinner. Okay, so U will identify for the field, and the V is for the antiparticle solutions. Okay. So now let's see what kind of algebra they follow. So if you take about the, for example, the energy part only, then we find out gamma 0 E minus M, okay, phi of x equal to 0. The energy part, if we think about, and then this will give you that E can have possible 2 choices, plus M and minus M. So we are the positive and the negative both. So that's why with the positive and negative, we can define my states, okay? And then we can define my EP having the positive energy solutions, another EP with a negative energy solution. Okay, so we'll not go into the philosophy of Dirac and all those things because we already know in the quantum physics there's a notion of particles and antiparticles. So that's why the E and minus C are involved here. But what I was saying that now the solutions will look like in this particular form. Okay, minus EIP dot X and VS E dot IP dot X. See, for the scalar case, you have only these two parts. But now for the fermion, because they should have a spin component, so these are the basically you will say the spin wave functions. Now, so the Dirac equation, if you write down in terms of these, solutions, what you will find out in the momentum space, this should look like P slash minus M USP equal to 0. Okay, and then P slash plus M VSP equal to 0. Okay, so these are the U and V are the basically conjugate spinors. Okay, and for the if you take a conjugation of that, then you will find out US bar, which is a function of P slash minus M equal to 0. Remember, in this particular case, US bar is basically similar as this is the definition I'm using, psi bar as psi dagger gamma 0. Okay, so this P slash is an operator, this acts from right to left. In this particular case, it was acting from left to right, but here it is acting right to left. Okay, that's how the action of the operator is defined. And similarly for the V spin also, the conjugate representations will have these relations. Okay, so this is how you write down these two relations, and they satisfy the following normalizations. You are dagger P US P equal to VR dagger P VSP as twice EP delta RS. That means the UR and US only can be combined together when they will have similar spins. That is dictated by the Kronecker delta. So R not equal to S, that will be 0, right? Similarly, for the antiparticle wave functions, we can write down US minus P equal to UR dagger P and Vs of minus T equal to 0. So particle antiparticle, when you write down, you get basically 0. So they are the basically this tells you from the quantum mechanical notion, you can think of this like a more like an inner product. So when we have this psi 1, psi 2 equal to 0, what does it mean? They are basically orthogonal, right? That means they are they are in a different kind of vector space they are defining. Similarly, U span a different vector space and V spans a different vector space, and they are basically independent, and that's it noted by this relation. Okay. So there, one of the important relations that we generally find out, which is basically in a covalent form, we can write down, which is US bar, not dagger, but so in a covalent form to write down US P equal to minus VR bar P VS P equal to twice M delta RS. So that's how we write down the covalent form. And also because these are the basis states, so like in quantum mechanics, we define these kind of operators. So here also you can do, but also if you remember, if there is some psi I outer product and I sum over I used to get identity, right? So keeping the similar thing in mind, so we get the position operator from here as sum over the spin USP US bar P equal to P slash plus M, and then S Vs P Vs bar equal to, or maybe yeah, equal to P slash minus M. So these are called the completeness criteria. Now this,
Professor,
yes,
I think there is a gamma factor missing on those spin sums in the results. If I remember correctly, it's gamma times P plus M and something like that.
which one? Which equation you talk about?
The last two equations, the last two spin sums, spinor
One?
sums.
This one?
The last two you wrote. No.
This one?
No. Below.
This one?
Exactly. I think there is a gamma factor multiplying both p's missing in that part, but I might be wrong.
No, so the gamma factor, okay. So gamma factor is basically not there because I have defined not US dagger. So if you write down a US dagger, then only the gamma 0 will be there. So I have
Okay.
absorbed the gamma 0 to define my US bar.
Okay, yeah. So yeah. So it's the slash, yes, you're
Okay.
using the slash notation.
Here, if you write down, so that's what I'm saying, that I am writing this is not in a covalent form, but now I'm writing in terms of bar, not dagger.
Yes, in terms of slash. I'm sorry, I just
Oh, no, it's
forgot.
okay. It's good to ask all of the question because I may miss some factors while writing because what I'm thinking and what I'm writing, maybe there's some kind of mismatch. So it's good. We always point it out. Thank you. Okay. So these are the completeness criteria, and these are very important because see what it is saying that you basically write down all the particles and somehow all the spins. Okay. So basically get the Dirac operator. Okay. So then later we'll see that when you talk about the, what's that? When you talk about the propagator of the fermion field, then this kind of relations will be very, very important. And then we'll see why the inverse of these relations actually give you the fermion propagator. So that's why these identities are important to understand that thing in a better way. Okay. So now we can check that gamma 0 is basically in a particularly, remember the form that I'm going to write for the gamma matrices are not unique. That depends on which basis you are writing. So here I'm using the Dirac-Pauli representations, and in these Dirac-Pauli representations, my gamma 0 look like this. The 4 by 4 matrices. So each identity matrix is actually 2 by 2. Okay, and gamma I is 0, sigma I minus sigma I 0. Okay, so this is a 4 by 4. And this is the definition of my Pauli spin matrices, which are 2 by 2 matrices, all of them minus I 0, and sigma 3 is 1, 0, 0, minus 1. Okay, so this is the representations I'm using. Okay. Okay, so now, okay, so one small task I would like to give you, that calculate gamma phi in these representations. So you know the gamma i's now, right? So gamma 0 you know. So basically I have defined earlier how this gamma phi look like in terms of the gamma matrices. Here it is. So now you should be able to plug in back and then see what is your gamma phi. Okay, so then you will get the feeling that trace of gamma phi is 0 or not and all those things. Okay. Okay. Another important identity, which is known as the Gordon identity, very useful to write it down. U bar P prime gamma mu U of P as 1 by twice M U bar P prime, and then you have a P plus P prime mu minus I sigma mu nu U nu U of P. Now you see, you will get the little bit of feeling about the sigma mu here. That what is this structure? Sigma mu, if I write down u bar p prime, sigma mu nu, q nu, u of p. Isn't it like a magnetic moment operator? Please go back and then check how to write down the magnetic moment of electron. You will see that this is the very much the operator. That's how you can generate that structure. Okay. And okay, it is Q. I must mention that Q is basically your P minus P prime. Okay. So now we'll define something which is called the projection operators for positive and negative energy states. So these position operators are basically defined as lambda plus minus equal to 1 by twice m plus minus p slash plus m. Right? And that is, we should not be surprised by that, because if you remember, here I mentioned that in this kind of outer product when you're writing, okay, then this can be used as a projection operator. And this structure, that what we have written here, is nothing but the outer product of the spin states. So their combinations can be possibly used to project out something. And if you see, what is this plus minus p slash minus m? These are nothing but these two possibilities that I have mentioned here. So this is nothing but the completeness condition of the U and V spinner, and that we are expecting to use as a projection operator for the project out positive and negative energy states. So that is the philosophy behind this operator, but we have to explicitly check their action. But before going there, if you have any question, please ask me.
But sir, how can we define for massless particle?
How can you define the?
Define the projection operator for massless particle. Can we define it any other way?
For the massless particle? For the massless particle, you cannot really discriminate these two, because then we work in a more like a helicity states. Okay.
Because for that particle, there are also positive and negative energy notion. So how can
Yes.
we distinguish those?
So that's why we define the wave function in terms of the helicity. Helicity is the position operator we use. Yeah.
Oh, okay, okay. Thank you, sir.
Because for the massive cases, helicity is not a good quantum number to define. So we cannot define for the massive case. Okay. Any other question? Okay. So
I have a question.
yes.
Well, no. We could leave it for the end of the class because it's a bit long. So
Sorry.
I think I guess it's better if I leave it to the end, towards the end of the class,
Sure,
because
sure. Yeah. After end of the lecture, you can ask the question.
yes, thank you.
Okay. Okay. So now there are a few identities that you can use, and this is the identities. They are not just given; they are consistent with the algebra that we have learned. Okay. And so please check these identities, because Fermion field theory, a lot of identities are there, and until you do that, you will not get the feeling. So I would suggest please do that thing. So A slash B slash, you can write down as a Q A dot B minus B slash A slash. So A dot B, when I'm writing, so A dot B stands for for notation. It's like this way. Okay. And A slash is a mu gamma, which is defined already earlier. And also you can check A slash equal to A square. Okay. And if you use these identities, what you find out, the lambda plus minus square is actually lambda plus minus lambda plus lambda minus equal to lambda minus lambda plus equal to 0, and lambda plus lambda minus equal to 1. Now you see, this is what is the property of the position operator. The position operator square is the position operator. Okay, and then if you were two different projection operators, they are independent. So that should, if you take a dot product or inner product kind of thing, I mean between them, you should get 0 because they are independent. So that's the cross check. And if you add both the position operator, you should get the identity. That means the whole vector you should regain. So these are the basically consistent definitions and the property of the position operator that we have learned in the quantum mechanics itself. So now what we can do, so lambda plus E acting on this USP is defined as the USP, and lambda minus over VSP is equal to VS. Okay. So now, if you see the why the coefficient are 1, because they are properly normalized states. That's why. If they are not properly normalized by 1, by twice, and so on, they will show up in these coefficients. Okay. And lambda plus V1, because if they act on the negative energy solutions, what I would expect? I would expect 0. Similarly, lambda minus, when they act on the US V1, I should get 0. These are the two set of conditions we can find out. Okay. And if I take a Hermitian conjugate of those structures, what I'll find out, US bar P lambda plus P bar equal to ES bar P, and VS bar P bar lambda minus P to VS bar P bar. So not only field but its conjugate field, they are also like that. And also we find out that VS bar P lambda plus P equal to US bar P lambda minus P equal to 0. So this is just the constant. Okay. So now, as someone asked a few minutes earlier, that if the fermions are massless, then what are the good choice of this position operator? So now we will see there is something called the helicity. Now, how do we define the helicity? Helicity is measured as the, is defined as the spin measured along the direction of, you can say, momentum or motion, considering that you define the momentum direction along the motion. Okay, so that's how you define your helicity. So the helicity operator is defined as sigma p, as sigma dot p. So this is the projection, and this is the magnitude of this thing, and this has eigenvalues plus minus 1. So that's why we call either positive helicity state or negative helicity state. Okay. So this sigma here we define as a sigma 2, 3, sigma 3, 1, and sigma 1, 2. Okay. And this is with the same spirit, the way we define the sigma mu nu definition as I by 2 gamma nu commutator. Right? So sigma 2, 3 would be I by 2 gamma 3 commutator. So from there, you get the component of this operator. So you know about this thing. So then once I define the helicity, then I can define my helicity projection operator as pi plus minus term as a half 1 plus minus sigma p. Okay. So that is how we define the helicity position operator. And once you define that, then you can check the following properties are satisfied or not. What should you expect? Pi plus minus square as pi plus minus, then pi plus pi minus equal to pi minus pi plus equal to 0, right? And then pi plus plus pi minus equal to identity. Okay, so that is how you can define this thing. Another important criteria is that lambda plus and the pi plus minus p, this commutator is 0 and also the negative thing. That means basically once you project out the basically your energy positive and negative in this thing, okay, so then the action of the helicity operator will not affect that. So the action of the helicity projection operator and the energy projection operator, they are independent. So that's something. Energy and helicity projection operators actions are independent. And as you know, in quantum mechanics, when the two operators commute with each other or among themselves, what we can do? We can choose a common eigenstates of lambda plus minus and then pi plus minus, right? So then we can define sigma p acting on USP as S is the helicity, USP, and sigma p Vs acting on P as minus S VSP, where S equal to plus minus 1.
Hello, sir. I have a question.
Yes,
Uh,
please.
Sir, when you define this complete set, a common set of commuting observable,
Yes.
projection operator is Lorentz invariant, but the helicity operator is not Lorentz invariant. Is there any problem to define this complete set?
No, because if in the helicity when you're defining, okay, so that's for the massless case. So that's also frame independent.
Helicity is frame dependent, right, sir?
Helicity is frame dependent for massive case. If it's a massless, automatically you are basically in the velocity of c. So you cannot go to other reference frame where you can change the velocity.
So,
That's
sir,
what,
when we define this common eigenstate,
yes.
when we define it projection operator, it is also for massless particle, massive particle.
No. The common eigenstate, that means the helicity cannot have an eigenstate for the massive case.
But projection operator defined for massive particle.
Projection operator, and the way it has been defined, okay, you have to take the limit m tends to 0 limit, and then you can define the proper normalizations. You can still define the projection operator for the energies. The energy that you have already mentioned, or you or someone has mentioned, right? That there's a En minus is still there. But this is not the immediate definition we can use, because we have to take the suitable limit m tends to 0 limit in a consistent way. Okay. You have to start with the massless Dirac equation. From there, you have to define the energy position operator. Right?
Okay.
For the massless case, I can define the position operator for the energy also. But certainly not that definition we cannot immediately use. We have to play with that structure and then we can define that. But the helicity we can define only for the massless, because otherwise the helicity will not be a good quantum number. It will be difference dependent. So when I'm saying that I'm defining both helicity as well as the energy position operator, that means I'm working in massless case.
Okay. So, sir, in this case, you are considering this projection operator for also massless case or massive?
For the massless case, yes. For the massless case.
Okay. Then it is consistent, right?
Yes.
Okay.
Yes.
Thank you, sir.
Otherwise, if you define a helicity for a massive case, it's not a good quantum number, right? For the
Yes.
massive case, we'll see we can define something the different kind of position operator. Okay.
Okay, okay.
So, any other question? Okay. So in the helicity position operator, then another position operator that we use, which is defined in an event dimension only. It will be clear. Chirality projection operator. So now, if we define a projection operator P plus minus as half 1 plus minus Q such that Q squared equal to 1. Okay, then automatically it satisfied that P plus minus square equal to P plus minus P plus P minus equal to 1 and P plus P minus equal to 0, right? Even without knowing detailed structure about the Q, we can get this operator and serve like a position operator. Now, using the property of gamma phi, we can see that gamma phi square is basically identity. So we can choose that Q to be my gamma phi. And there we define something called PL and PR, which is 1 minus plus gamma phi over half. So L stands for left hand or left chiral, and R stands for right hand or right chiral. Okay, so these are the chirality position operators. So these will also define as a pi minus of P, or in the massless limit, the chirality operator and the helicity position operator, they are basically the same. So this is how we can still define this thing. So that's the important part. For massless case, your chirality and helicity are same, similar way. But for the massive case, you do not have a good helicity operator because it depends on reference frame. But you can certainly define the chiral operator. And that's why for the massive fermion case, we'll define and we'll work with the chiral position. Now you see, this chiral position operator we can define only when gamma phi is not part of the Clifford algebra. And that is when we are working in event dimension, right? So that's why these projection operators can be constructed only in the event dimension, event space-time dimension, okay? Such that when you write down the total fermion representations, okay, the total fermion representations can be divided into two equal half. One will be transforming as a left chiral fermion, another half will be transforming as a right chiral fermion. And remember, the left and right chiral dimensionality would be the same. Okay, is that point clear? Okay. So that's another kind of position operator, which is called a spin projection operator, and that we will not immediately use. So we'll revisit that whenever required. So now we'll look into the Lagrangian for a Dirac field. Okay. So this is written as a psi bar I del slash minus m psi. Okay. Now you can ask me where are the spin indices? Here the spin indices are summed over. So if I write down explicitly the spin indices, this equation will look like psi bar alpha, then I, gamma mu, alpha beta, del mu, minus m delta alpha beta phi beta. So delta is a space-time operator, so it doesn't have any kind of information about the spin. So spin space in the Clifford space is different than the space-time space. So that's why del mu doesn't contain any kind of spin in this. But the gamma matrices actually carry the signature of the space-time information, the representations. That's why they have the spin indices here, alpha and beta. And alpha beta are basically the the spin indices, you can think of that way. Now, if you find out the Euler-Lagrange equation, what we find out the following. Euler-Lagrange equation. So del mu delta L delta of del mu psi alpha bar minus delta L del psi alpha bar equal to 0. And if you do that, what you will find out is the Dirac equation. Right? That's how you write down the Dirac equation. Okay. So now you might be wondering that, okay, so I write down the Lagrangian for this part, for example, it is acting on I by 2. So these are the possible form of Dirac equation you can write down. Then mu psi, and then this del can also act on this psi bar, so that I'll write down I by 2 del mu psi bar gamma mu psi, and then minus m psi bar psi. And then because we know the Lagrangian is basically Hermitian, so from there, if we can subtract these two Lagrangian, okay, let me call it L prime. So then if we calculate my L prime minus L, okay, so what I'll find out is the following. Del mu of I by 2 psi bar gamma mu psi, maybe a minus sign. Please check this sign. I've defined my Lagrangian here. I define my L prime, which contains the equation with respect to particle and antiparticle both, and the mass term. So if I subtract these two, what I'll find out that this deviation is something del mu times this quantity. And what is this quantity? This quantity is basically called the current, and noted as J mu is basically proportional to psi bar gamma mu psi. And that's how we introduce the Fermion current. And because we know the current is basically conserved, okay, so that del mu J mu is basically 0. Now, when there is no source term, the current is conserved here, and also the theories are anomaly and so on. At this moment, they are not important, but with a tree-level current, you can think of that way. Okay, so del mu J mu equal to 0. Okay, so that's why whether you write down Lagrangian in this particular form or this particular form, they are basically equivalent. So what we learn from here, that if I have a Lagrangian and then I modify my Lagrangian by a total derivative term in such a way, okay, that if I take an integration of this total derivative term in the action, that will vanish at the infinity. Okay, so that's why a Lagrangian and its total derivative term are basically equivalent within the framework of field theory that we are working with. That's why either you work with this Lagrangian or that Lagrangian, your things will not alter. Okay, any question? Okay, so now from here you can define something called the charge Q, which is defined as the dqx J naught, and then you see it is proportional to psi dagger psi, right? And what is this psi dagger psi? When they act on the charge state, they are basically the number operators. So that's what you expect. number over the whole volume, you get the total amount of charges, right? That's right.
Professor,
Yes.
isn't it the expression you just obtained for the current, for the conserved current, doesn't also come as a result of the Noether's theorem?
Yes,
For
yes. Yes, exactly. You are absolutely correct. But I am not mentioning explicitly Noether's thing because my plan is to basically talk about the Noether's theorem when you talk about the symmetry and all those things. So there,
Okay,
so I'll do it. Start with the scalar field theory. You can scalar field theory also has a current and all those things, right? So you can calculate those things. Conserve quantities from there, Noether charges and all those things. We'll revisit, we'll do that thing, and then using that formalism also one should be able to calculate the current in this particular form. But you are absolutely correct from the Noether's current. But as I have not taught yet the Noether's theorem and all those things, so I was avoiding that term. This is just from the total derivative explanation. I was trying to explain the presence of this current.
thank you.
Yeah. Any other question? Okay. Okay, so another point I will mention here, but we'll again talk detail. So basically the notion of the spin, why is this coming from? There is something called the Pauli-Lubansky operator. Lubansky operator, which you write down. Remember, this is not W mu of the gauge boson or something like that. This is just a definition of Pauli-Lubansky operator, which you write down, introduced in this particular form, mu nu lambda rho and mu nu j lambda rho. P is the pole momentum. Okay, so this is the, and this is the S mu nu. So if you calculate this W mu, you get this eigenvalue S into S plus 1. So this S is the spin. So that's why from the Lorentz transformation, we can define this one of the Casimir operator. Okay, and which contains the information about the spin. Okay, so that's how the spin information is hidden in through this operator in this Lorentz symmetry information. Okay, but when talking about the Lorentz group representations, we'll revisit this.
What is the J lambda rho? It is the generator.
J lambda rho
Lorentz
is the
generator.
Lorentz group generators actually, yeah.
Okay.
Okay, yeah. Up to this part, any question? Okay, so now let's go to the decomposition of fermion fields. This we have done in the context of scalar. So we'll do very similar thing for the fermion case. Let me write down and then see if we revisit the scalar part, what are the exact difference? And that is what I mentioned in the very beginning of today's lecture. Is dqp by 2 pi q twice eq and then some spins. As we are working the spin half, so we have only two polarizations. That's why spin equal to 1 and 2. Okay, when I'm saying S equal to 1 and 2, please do not consider that spin is 1 and 2. The spin indices are 1 and 2. One is for plus up, one is for minus in that way. Okay. Fs of p, of p minus IP dot f, but Fs is the other p ds of p, but IP dot x. Right. So now, if you try to recall the scalar case, what did we have? we had those free particular function of the planar solutions accompanied by the creation and annihilation operator. In this particular case, we have this creation and annihilation operator, right? But on top of that, because they are the spin field, non-zero field, spin-off field, that's why there is some solution for the spin wave functions should be there, and these carries the information about the spin wave functions. Agreed? And then when I'm talking about the creation and annihilation, we have to also remember that because they have the spin, so any arbitrary spin creation cannot be equivalently written as a annihilation operator of the antiparticle. They should have the similar kind of spin. That's why there should be a spin tag with this creation and annihilation of the field operator. Right? That's why they are Fs and Fs tag. So when I'm calling a fermion creation is equivalently antiparticle, anti-fermion annihilation. And because to track back their spin are correctly noted, we have to tag those creation and annihilation operator with the spins as well. That's why they are Fs and Fs tag.
Sir, I have a question.
Yes.
For curiosity, can we use the chiral quantum number instead of the spin quantum number, because chiral quantum number is also intrinsic to the particle.
No, spin is also because this I am not mentioning this. I am working in a 3+1 dimension or in any other dimension. Chiral is very specific to event dimension first of all, right? And these are
Yes,
these are the Fourier modes. So these modes that psi, the chiral operator acts on this side. Okay, and then they will be decomposing, different kind of chirality.
no, then they also act on the spinor, right?
So
U
they
and V
will
spinor.
act on the spinors in a sense because they will not act on the spinors on set way. They will set up the relation between U and V. Okay. So here, when I'm writing psi, let's say 4-component object, you have to write down US also 4-component object, V also 4-component object. But if you use the chiral position, then you can write down U and V into 2-component way. Okay. And the left and right, they are related by kind of a conjugation, and so those kind of relations will be set up. So at this moment, using the chiral operator will not be much useful because this decomposition is independent whether I have a chiral representation or not. Chiral representation is very specific to the event dimension, but this decomposition is independent whether you are working in event dimension or odd dimension. This is a more fundamental decomposition.
Okay.
Okay.
Thank you, sir.
Yeah, you can add chiral operator on this thing. You can add, but those are the projected space. This is not projected space. This is just from the creation and annihilation point of view. On the same way that we introduce the scalar fields decompositions. Okay.
Okay, sir.
Okay. So now the same speed we can write down the conjugate field psi bar as dqp by q by q by qp, and then our spin, two spin polarization states. So now the projection, so dagger of that, so Fs dagger of P, so US dagger will be there because now the gamma 0, so that becomes your US bar. It becomes into the bar I. You take Fs P VS bar P minus I. Okay. So can you hear me? Hello?
Yes.
Yes, okay, good. So yeah, so this is how you define this thing. And then you can calculate the total Hamiltonian H as your d cube x del L del psi alpha dot 1 dot x minus L. And from there, you can find out the total Hamiltonian density. From there, my gamma dot L plus M. Okay, so this is the total Hamiltonian density. You can find it out in this particular form. And then what you do actually, you plug in your psi and psi bar from these decompositions. And if you do so, you should be able to write it down in terms of number operator proportional to the energy, like in the harmonic oscillators, what we have done. So please do this as a homework. This is simple. Minus f of tilde. By P. Okay. So this is how you define the number operator for particle and antiparticle. So sum over all the spins. So this is number operator times your energy, so you'll get the total energy. Okay. And also your quantization relations gives you we got prime this dagger P prime plus equal to, so you have a quantizations for particles and antiparticles separately, right? Similar to the scalar case. So if you remember, the quantization was related in terms of A and A dagger and B and B dagger. There is no A and B dagger. With the same spirit, we can write down for the F and F dagger and F hat and F hat dagger. So this quantity prime dagger and plus we have a delta S prime Q minus Q prime. Okay. And then you can write down your normal ordered harmonic system Hamiltonian as D2P, EP, F polarizations are there, Fs dagger P, Fs P plus Fs dagger hat P, Fs hat P. The annihilation operator will be at the right. So that's how you define the normal ordered Hamiltonian. So this is the for the Fermion case, we can define this thing. Okay. Is there any question? So this structure is basically very similar what we have done for the scalar case. That's why we did the scalar case earlier. And then only little bit of departure from the scalar decomposition because we have the spins. That's all. And we have to remember these are all in terms of the anti-commuting. So Fermion quantizations are related in terms of the anti-commutator because fermions have a non-zero spin, they satisfy the Clifford algebra, and Clifford algebra is described in terms of the anti-commutator. That's why it's a plus sign. But for the bosonic fields, this is a commutator. That's the few key points you should always remember in your mind. Then I think it will not make any mistake. Okay. Okay. So now what we'll do for the scalar, we have defined the Green's function, if you remember, right? Similarly, without going into too much detail like the scalar, because the structure is basically the same, we can define the Fermion propagators. Now, how do we define the propagators there in the momentum space? If you take an inverse of the Fourier transform of the operator, keeping in mind the inverse of the operator exists. This is very important because when you do the abelian case, you will see that's the most challenging task because there's a singularity in that operator. We cannot set the massless gauge for E1 abelian case at least. Invert the operator, so we cannot directly write down the propagator. We have to do something related to that. We learn that thing. But for the Fermion case, we can invert the operator. So that's why we can write down the propagator in a very systematic way, very similar to the scalar case. So that was my Dirac equation. If I have any kind of source term, then this is the modified Dirac equation. Okay, and then the Dirac propagator we introduce in the following way. Gamma mu del mu x minus m is f for the fermion, or when we put f for the fermion, x minus x prime is del 4x minus x prime, right? That was the definition of the propagator we used. And then the solution of the Dirac equation is basically psi of x. You know, using the Green's function technique, we can easily write down d4x prime sf of x minus x prime g of x prime. Okay. And then we can write down the solutions x minus x prime as d4 p by 2 pi to the power 4 e to the minus I p dot x minus x prime s of p. Okay. So if you plug it back in this relation, what you should find out that p slash minus m sf of p must be 1. Then only it will be consistent. So now what you do, you apply p slash plus m operator from both ends. So p slash plus m, p slash minus m, of p equal to 1. And then now p slash plus m becomes p square minus m square. This is exactly the similar structure that you find out for the Klein-Gordon operator, or Klein-Gordon field, right? Sorry, there's some p slash plus m will be there, p slash plus m, this is p slash plus m. So I can invert this operator and I write down momentum operator p slash plus m by p square minus m square. So this is my fermion operator. Okay, and what is this p slash plus m? So you can write it down as a 1 by p square minus m square. Now us of p, us bar of p. Remember I told you that we can use this to rewrite the fermion propagators in this particular form. Now when you have to write down the antiparticle propagator or the antifermion, you replace this u by ds of p. So then you don't need to remember that it's a p slash plus m or minus p slash plus m or whatever. You can just remember that if you in this particular form, if you write down the propagator, you just change your u by v. And now you see when you talk about the Dirac spinor or Marronov spinor, for the Marronov spinor, you know how an u and v are related. You just use this relation. So for any kind of fermion, you should be able to write down the propagator. So that's the unified description. We should be able to write it down. And in the position space, this can be written by using the Fourier transformation. So you write down the d4p by 2 pi to the power 4 to the minus ip dot x minus x prime, and then sf. So you can write it down as a delta f x minus x prime. Okay, so delta f is basically the propagator. Okay, let me not put it as f here because this is a fermion, not Feynman propagator for the scalar. Right? In this way, you can write down your Feynman propagator in the position space. Now, if you remember the scalar propagator, we have written down in a time ordered way. So we should be able to write it down here also. So this is nothing but I sf x minus x prime is written as a now dq by twice pi whole cube twice ep. So this theta function is very similar what we have introduced for the scalar case. That's m to the power minus I p dot x minus x prime minus theta function t prime minus t plus minus m e to the power I p dot x minus x prime. Okay. So when you have this now time order product of the psi alpha x psi beta bar x prime, how do you write it down? You write down psi alpha x psi beta bar x prime if your t is greater than t prime, and then this is minus psi beta bar x prime psi alpha x if your t prime is greater than t. So that's how in the scalar propagator for the complex scalar field, how to write down time ordered product. Just mimic this thing. Only thing remember, the minus sign is because the fermion fields anti-commute among themselves. So when they pass through each other for going from t prime greater than t, they become minus sign. So that is the origin of this minus sign. Is basically signature of the anti-commuting nature is basically reflected from there. So this is how you define your fermion fields and the quantization, the propagators, and all those things. So now we are ready to introduce the fermion and scalar field theory together. And the next class we will introduce the how the scattering of Yukawa kind of interaction where fermion field interact with the scalar field and how to do the amplitude calculation and all those things in general. That will be the next class.